Namaskar, I am Dayan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the complex analysis. First topic is complex numbers from MSC Part 4, Semester 2nd, new syllabus Semester 1st, and first topic is complex numbers. Complex number is nothing but negative or square root of negative number does not exist in the real number system. Therefore, complex numbers arises. Complex number is arises for the square root of the negative square root of the negative number. We know that the equation x square plus a is equal to 0 has no solution. The leads to the introduction of complex number in which equation of the form x square plus a is equal to 0 where a greater than 0 have solutions. This chapter introduces complex numbers, their representations and basic properties. Definition. First, the complex numbers can be defined as a pair of real numbers xy such that xy belongs to our real number equipped with additions xy plus ab is equal to x plus a y plus b, and multiplications are being defined as xy into ax ab is equal to xa minus yb xb plus ya. One reason to believe that the definitions of these binary operations are good is that is an extension of, in the sense that the complex numbers of the form x0 believes be of the like real numbers, and x0 plus a0 is equal to x plus a0, and x0 into a0 is equal to xa into 0 xa0. So we can think of the real numbers being embedded in as those complex numbers whose second coordinate is 0. The following basic results state the algebraic structure that we establish with our definition in proof of straightforward but nevertheless a good exercise. Commutative law for additions. Z1 plus Z2 is equal to Z2 plus Z1. Associative law for addition. Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. Additive identity. There is a complex number Z such that Z plus Z0 is equal to Z for all complex numbers Z. The number Z0 is an order pair 0 0. Additive inverse. For any complex number Z, there is a complex number minus Z such that Z plus minus Z is equal to 0 0. The number minus Z is minus x minus y. Commutative law for additions. Z1 multiplies Z2 is equal to Z2 into Z1. Associative law for multiplication. Z1 into Z2 into Z3 is equal to Z1 multiplies Z2 into Z3. Multiplicative identity. There is a complex number Z such that Z into Z dash is equal to Z for all complex number z. The number z dash is an order pair 1 0. Multiplicative inverse for any non-zero numbers complex number z. There is a complex number z inverse such that z into z inverse is equal to 1 0. The number z inverse is x divided by x square plus y square minus y divided by x square plus y square. The distributive law z1 into z2 plus z3 is equal to z1 into z2 plus z1 into z3. If you write x for the complex number x0, this mapping x to x0 defines a field isomorphism of into, we may say, so we may consider as a subset of if we put I is equal to 0 1, then z is equal to x0, xy is equal to x0 plus 0y, x0 plus 0 1 into y0 is equal to x plus iy. This by x is equal to real of z, y is equal to imaginary of z. If x is equal to 0, the complex number z is purely imaginary, and if y is equal to 0, the complex number z is purely real. Note that 0 is the only number which is at once real and purely imaginary. Two complex numbers are equal if and only if they have the same real part and the same imaginary part. Complex plane or organ plane. The number z is equal to xy is equal to x plus iy can be identified with the unique point xy in the plane. The plane representing the complex number is called the complex plane. Now here in x axis, this is real axis, and y axis, this is imaginary axis, and coordinate z is equal to xy is equal to x plus y situated at first quadrant. Definitions: let z is equal to x plus y, xy belongs to R. Then the complex number x minus y iy is called the conjugate of z and is denoted by z bar. Following are the basic properties of conjugates. Real part of z is equal to z plus z bar divided by 2, and imaginary part of z is equal to z minus z bar divided by 2i. Z is real if and only if z is equal to z bar. z1 plus z2 conjugate is equal to z1 plus z1 conjugate plus z2 conjugate. z1 into z2 conjugate is equal to z1 conjugate into z2 conjugate. z1 divided by z2 conjugate is equal to z1 conjugate divided by z2 conjugate if z2 is not equal to 0, and z closed conjugate of conjugate is equal to z. Next definition: let z is equal to x plus iy, xy belongs to R. The modulus or absolute value of z is not negative real number denoted by modulus of z, and is given by modulus of z is equal to x square plus y square raised to 1 by 2. The number modulus of z is the distance between the origin and the point xy. Following are the basic properties of modulus. Modulus of z square is equal to z into z bar. Modulus of z1 into z2 is equal to modulus of z1 into modulus of z2. Modulus of z1 divided by z2 is equal to modulus of z1 divided by z2 if z2 is not equal to 0. Conjugate of z1 into z2 is equal to z1 conjugate multiply z2 conjugate. Z conjugate is equal to modulus of z conjugate is equal to modulus of z. Modulus of x is equal to modulus of real of z is less equal modulus of z, and modulus of y is equal to modulus of imaginary of z is less equal modulus of z. Modulus of z1 plus z2 is less equal modulus of z1 plus modulus of z2. Modulus of z1 minus z2 is less equal modulus of z1 plus modulus of z2. Modulus of z1 minus z2 is greater equal modulus of z1 minus modulus of z2. Let z1 is equal to x1 plus iy1 and z2 is equal to x plus x2 plus iy2. Then modulus of z1 minus z2 is equal to x1 minus x2 plus I into y1 minus i2 is equal to x1 minus x2 bracket square plus y2 minus y2 bracket square raised to half, which is the distance between the point x1 y1 x2 y2. Hence the distance between the point z1 and z2 is given by modulus of z1 minus z2. Polar representations of the complex numbers. Consider the point z is equal to x plus iy. In the complex plane, this point has polar coordinate r theta, where x is equal to r cos theta and y is equal to r sin theta. Then z is equal to x plus iy is equal to r into cos theta plus I sin theta. Clearly, r is equal to modulus of z is equal to x square plus y square raised to half, which is magnitude of the complex number, and theta undefined if z is equal to 0 is the angle between the positive real axis and the line segment from 0 to z, and it's called the argument of z, denoted by theta is equal to argument of z. We note that the value of argument of z is not unique. If theta is equal to argument of z, then theta plus 2 pi n, where n is the integer, is also argument of z. The value of argument of z that lies in the range minus pi to plus pi and is called principal value of argument of z. If z1, z2 is called principal value of argument of z.